Starting with this video, we will begin to work with models of the data. By models in this video, we are talking about linear models, slightly nonlinear models, and then two types of machine learning models. A lot of the beginning part we've already seen. Let me start with the first thing that helps a little bit. This RM says remove, and list equals ls. This says list out all of the things that are in your environment. This ls is the environment function. So remove everything that's in your environment. If you run this, it'll remove everything over here that's in your environment. So if you've accumulated a bunch of things over here that you don't want anymore, you can clean that out. We've seen the package readr, dplyr, ggplot2. Towards the end of the video today, we will start working with two new packages, this caret package. The caret package is a machine learning or training package, so it will train different models and go through the parameters of those models to try and find some optimal model. And you can find information about it here at this website, so if you want to go look that up, it has a lot of information and there are lots of models. We will just use a couple of those today. And this package here, do parallel, if you have a computer that can handle it, you have multiple cores, or something we won't cover here, but if you have a cluster of computers that you might want to send a program off to, we can run some things in parallel, and we will do that with the caret package as well. These functions we already have talked about, so I will run these, but we won't talk about them more. I have a new data set, that is growthdata.csv, and if we run it, we can look at what it looks like. So it's sort of the same format as the last data set. We have all of these company names, we have the year that their data came from, and we just have some major topics of accounting information, their revenues, their total expenses, their assets, and their liabilities. What I want to try to work with in this data set is predicting 1 year ahead revenue growth. So we'll create those variables, and the things that we have as potential predictors will have to come from these variables here. So first we'll create the variables. We've done this a few times now, so I won't spend too much time here, but we're going to predict revenue growth. Notice this is lead. This is the only thing in here that has a lead in it. That's because we're going to predict 1 year ahead revenue growth, which is this right here. The variables that I thought we could use would be lagged revenue growth or revenue growth from year T, expense growth, asset growth, and liability growth. So something, fairly straightforward. Then we ungroup it, remove all the missing values. This is a different way than using the miss function than we've used before. The dot means the data set that you're working with, so we can apply it in this way. Then we're going to remove the outliers. Here I'm removing the outliers by year. And a new function, select, that says keep only columns that I name in the select function. So here I'm only keeping company name, year, and these variables that we just created, these new columns. So I can run these, and we can look at the data and see what it looks like at this point. So notice I went from about 45,000 down to about 24,000. That is primarily because I'm requiring non-missing values for next year, and these growth variables require 2 years, so we lost some years. So notice we don't have 2015 in here. That's because that was the first year. But everything else, we have the company names and everything we need here, a bunch of growth variables. If we do the summary, we can take a quick look at what the variables look like. So we have from 2016 to 2019, the revenue growth goes from minus 100% to 500%. So even though we took out some outliers, we still have some very large values. So most from the first quartile to the third quartile were between -5% and positive 17%. So these ones on the outside are really large still, but they're brought in at least a little bit from what it was before. and the same thing goes for these other growth variables. The only sort of weird one is that we have this negative 200% expense growth. That's because some of them have negative expenses in the data set, which is a weird concept anyway, but oh well, it's there in the data. So then the first thing we have to worry about when we're going to train a model is we need to mess around with the training data, and in linear regression this isn't always really necessary if we have all of the variables that we want to include in the model. But when we're dealing with machine learning models, we need to find a parameter that seems to work well for the data. So we need to keep that out of the data that we're going to use to evaluate the model. So I split this here into a training data set. Capitals TRN is what I'm referring to as training. Capitals TST is what I'm referring to as the testing data. And there are multiple ways we can split up data into training and testing. Here I'm doing it by year. So the training data, I pull out only years before 2018. So that would be 2016 and 17. And for the testing data, I'm going to only pull out years after and including 2018. So that would be 2018 and 2019. So I run this. Now I've got two data sets that I can work with. There are other ways we can do that. The way I will use for the rest of the video is this random sample. So let's look at that. So anytime you're doing a random approach, if you repeat it another time, you won't always get the same solution or answer. So we can set the random production of those random variables. So that's by setting the seed. You can put in any number here, and as long as you put in the same number, it's going to start the random variable the same way. So I'm going to set the seed, and this is going to apply to a bunch of the random things we do later. Then I can randomly sample from the temp2 data set, and sample underscore frac is the sample fraction from the DPLYR package, and I'm going to sample 60% of that data set. So I pull that. Now it is 14,000, which is about 60% of this 24,000 one. So then with the DPLYR framework, I can also join and merge data sets. And so this is the first time we're going to do a merging. It's a really simple version, but we could do things in different ways, which at some point we'll do. But I'm going to start with the temp2 data that I created before, and I'm going to anti-join the training data. So there are other joins you can do, but I'm going to anti-join, meaning from the temp2 data, only pull in things that do not show up in the training data. So test gives me everything else except for what's in the training data. And this is about 40% then, so we've got 9,600 observations here. So now I've got a training data, a testing data. And if I'm going to be doing a lot of things that require a lot of RAM and memory, I might just remove some things that I don't need now. So let's say I remove these two data sets that I already worked with. So I remove temp and temp2. Now I just have the training and the testing data. So let's start with our first model. This is the simplest model, linear regression. This is OLS, ordinary least squares. And the command is LM. This is the LM function, linear model. And let's talk about sort of the basic setup. So we start with the Y variable. This is the thing we are trying to explain or predict. To tell it it's a model, that's this tilde sign. So that's on the top left of your keyboard. And the X variables we put in together with plus signs in between. So revenue growth is one of the columns, expense growth is another, asset growth and liability growth. Then after the comma, we need to tell it what data set it comes from. Here it's TRN, that's our training data. And it will estimate a linear regression model. So I'm saving that model to the object called EST. That's my way of saying estimate. So this is my model estimate or estimation. So I run that. What you see up here is this EST. This is a model results object that tells me what that model looked like. Well, we can do a simple way to look at this is do the summary. and it's going to show us the results from this linear regression model. So for those of you that haven't looked at them in a little while, let's try and explain what the linear regression model means. One of the benefits of a model like this is that we have a way to explain what's going on, whereas when we get into the machine learning methods, we don't have something that is quite as easy to understand. So the Y variable is next year's revenue growth. This column here, the estimate column, are the coefficient estimates. So these are the slopes that are estimated on these different columns. Okay, so we have revenue growth, and the slope here would be 0.06. So in an XY graph, if you remember what you memorized maybe when you were in elementary school, so something like y equals mx plus b, where mx, so m times x, the x is the variable and m is the slope. Well, this is the same thing. This is the slope estimate here. And another way to think about them is you can think about them as partial derivatives. So as revenue growth changes in year t, how much does revenue growth year t plus 1 change, keeping everything else constant? Well, that would be this 0.06. So as revenue growth changes by 1 this year, next year's revenue growth changes by 0.06. That's not terribly great, right? If you grow by 100% this year, the association is next year you grow by 6%. Not fantastic, but that sort of reflects the idea that growth doesn't continue strongly. Expense growth, so then let's talk about over here. Notice over here, the easy thing to spot is there are no stars at the end of the row here. R and some other packages put things like stars here to indicate that they're statistically significant. No stars here is supposed to indicate that this slope estimate is not any different from 0, at least statistically. And how we see these is based on all of these other columns. So 3 stars is highly significant. What that means is compared to this estimate, so here I'm looking at the intercept, compared to that estimate, the standard error is really low, which then, because this standard error is low, that means that this t-value is high. So t-value is, one way to think about it is when you're doing a hypothesis test, how far away on the edges of a normal distribution is that value. So if you want to go look up t-values and how to do hypothesis testing, you could go look that up. That's the main thing that we're relying on here. But a large t-value, either large positive or large negative, would indicate the coefficient estimate is statistically significant. So then this is the probability that this is not significant. So this is very close to 0, so then that would be statistically significant. So notice what happens then here in the expense growth column. We've got a small t-value. So when we're thinking about large, we're thinking about something close to 2 or larger. And we have something that is closer to 1 than it is to 0, so this is large, not significant. Now let's go to talk about the other coefficients. So this one we think is statistically indistinguishable from 0. These ones are statistically significant. What does that mean? So if you had asset growth, let's say 100% asset growth in year t, that tends to be associated with, so the partial derivative is 0.12, so meaning if you had 100% asset growth this year, next year the association is 12% revenue growth in the following year. Same thing with liability growth. If you had 100% liability growth in this year, you have 14% revenue growth in the following year. So these are the associations that we're thinking of. Let's talk about that in terms of economic terms. So if you had some sales growth in the past, you tend to continue at least a little bit having sales growth in the future. If you invest a lot this year, you tend to have higher sales next year. if you took out a bunch of debt this year, you tend to have higher sales this year. This one's a little bit weird, right? Because the asset growth, you think of investing, and that turns into something where you can make more revenue. Well, the liability growth, why that's positive is most likely because you add more debt when you anticipate that you're going to have future revenues, or because you're taking out debt to invest more so that your revenues will grow. Okay, so the benefit of these linear models is we can interpret these slopes and try and understand how things that are our x variables are associated with the y variable. We're going to talk about model fit in the next class, but let's just mention this quickly. So we have these r squared values. R squareds are how closely the x variables fit the y variable. So if it's 100%, we would have 1 here. If it's 0, we have 0. So 7% r squared. For some of the variables like growth and returns and other things that we would look at, that's a really nice r squared. But if we're trying to think how well can we explain it, 100% is much greater than 7%. But there are some trade-offs and some things that go into this as we talk about fit next class. Okay, so then let's talk about how we get predictions out of that. So we have this model. This EST is our model. On the training data, we created a model that picks up the patterns in the x and y variables in training data. So we haven't used it to predict anything, but we created a sort of line or multi-dimensional sort of line or plane that captures these patterns. So then we can use those patterns and see how that fits the data. So let me do two things. We have this predict function. That isn't saying it predicts. What it's saying is take this model, this EST model we have, apply it to this TRN data set, and use the model to come up with what the y variable would be based on that model. So if we go back to what came out of this, this means for a given row, so let me open this up here. So if we have Teton advisors, let's see how we would use the model to come up with what the y value should be given that we have this model. So how would we do that? This is the actual y value, but we want to come up with what we would predict based on this model. So this is just the equation for a line, just like you would do in an algebra or geometry class. So we have the intercept. That's when all the x's are 0. Where does the plane or the line cross the y-axis? So here, when all of these are 0, the intercept is 0.07. So that is our first thing. The intercept plus, and then thinking about the slopes and how they work, it is this slope, this is the slope, times, notice it's the slope on revenue growth, times revenue growth. And then we do the next thing. So then slope on expense growth times expense growth here, slope on asset growth times asset growth, and slope on liability growth times liability growth. Multiply those together, add all of those up, just like you would in an equation for a line. That gives you what the model would say this revenue growth would be. So when we run this predict function, the only thing it's doing is going through that algebra to create a prediction for the y variable given the model that we have. So if we run this, then what you will see in this training data set is at the end we have what I'm calling the fitted value. This is the prediction for the y variable, so what revenue growth would be next year given the model we have, all those slopes and the intercept, and these observations for this company. So in this case, we see 2016, or this is for the next year, so 2017 revenue growth was 120%. What the model says it should be is 12%, so we're way off there. We have a couple of examples here. This next one, so Cohen and Company, the model fits and says it should be 31% growth. It was negative 14% growth, not doing so good here, right? Well, here, maybe we get a little more lucky here. Let's choose a couple where it kind of works. For this financial corporation, it says it should be 11%. It actually ends up being about 16%. We're not too far off there. Let's try this other one, the Mechanics Bank. 24% is what the model would say it should be, and we get 55% was what it actually was. So notice we're not nailing it, right? That's the 7% R squared issue, that the model can't pick up all the variation that is actually occurring in revenue growth, but at least the sort of pattern is there. And notice this is where we estimated the model, so it has to be at least somewhat associated, this fitted value and this revenue growth, because that's how we estimate it. So then the real question is, when we use these patterns in the data to predict on new data, how does it work? So then how we would go about doing that is we do the same function, predict, using the model that we estimated on the training data. Now go ahead and do the same application using the testing data. So again, collect the columns that are in the testing data and apply the slopes and the intercept to that to come up with what we would predict. So to make it easy to remember here, the fitted value I'm using as the training data Y variable that the model would say the Y variable should be, but when we're actually going to try and predict it, that's this testing data and the predicted column that I'm creating. So if I run this is new data, so I go ahead and look at the testing data. At the end, we have this predicted value. And we could see for 1-800-Flowers.com, the actual growth in 2020 was 19%. Remember, this is 2019 is year T, so this is for the following year. And we predicted that it would be about 9%. So the prediction in that case was not too off. In the 10 times genomics company, the revenue growth was actually 68%. The model predicts 55%. So again, not too far off of what it should be. But then to humble us a little bit, the revenue growth here for this 180 degree, I don't know what that is, but that company was minus 44%. And we had the predicted value of 10%. Yeah, we failed there. All right. And I guess something I forgot to talk about, let's go up here. Notice here, this is a different data set, so I am sorting by the company name and the year, and I'm grouping by company name because we have different columns in the data. Okay. All right, so this is our linear model. We have some fitted values and some predictions. One question would be, how good are those? That's what we're going to work on in the next class. So let's move on to some other possibilities. Well, if you remember quadratics and how you come up with lines in your geometry class or algebra class, well, we can add quadratic parts to the equation to make something not linear. So remember, if we have a curvy line, that would include x and x squared and maybe x cubed, or if we want to have a circle sort of shape, that's an x squared. So these polynomials, you could add lots and lots of these, and it would allow the line or the plane to not be just a straight line. So here I'm going to create revenue growth squared. Each of these x variables, I'm creating a squared version of those. Notice then I include revenue growth and revenue growth squared, expense growth squared, etc. And that it's the same thing other than that. So we can go ahead and look and see what that looks like. And just quickly, revenue growth before was positive. Notice this flips to negative once we allow for the nonlinear relation. So it used to be modestly positive, right? So if I'm pretending I'm drawing it here, it goes up a little bit. Well, here it would say it actually goes down, but then curves upward a little bit. So we've got this sort of downward slope that curves. And it's both of those are significant. Expense growth is still not significant, but the squared term is significant. So apparently there is some nonlinear relation between expense growth in T and future revenues or future revenue growth. Both the asset growth ones still are important, and they're both positive, so it's sort of, a positive slope, but then positive and increasing. And then liability growth, only the linear effect matters, the nonlinear part does not. We saw the R squared before, now it's gone up a little bit. It's not a tremendous increase, but a slightly higher R squared. Another way to add nonlinear or nonlinearity to the linear regression is to interact terms. So what this allows the line to do is to change the slope across different x variables. So let me try and explain this. This takes a little bit of time, and we could look at it on a simple graph, but let me just quickly do it here. So revenue, all of these ones are positive revenue growth, expense growth not anymore, or never was, asset growth and liability growth, same thing. So then do any of these nonlinear things matter? Well, and by nonlinear I mean interactions. Revenue growth with asset growth, nothing. But revenue growth with liability growth, that seems to matter. And expense growth with liability growth also seems to matter. So let's talk through sort of what this might mean. So how we interpret these is the slope on revenue growth depends on the liability growth. So holding constant how much the liability growth is, then the higher the revenue growth you have, the higher the future revenue growth is. But by increasing liability growth, we're also increasing the effect of revenue growth. And then notice expense growth didn't matter by itself, but when you include expense growth and liability growth, it is negative. So another way to think about that is if your expenses were going up and you had debt that's going up, this means lower revenues in the future. I think what this could mean is that you are having a company that is growing both their expenses and their liabilities. You might increase your liabilities to help cover your expenses, not necessarily to grow your revenues. So a little bit complicated, but the main part is that I want you to think about is then how does this matter for the model? Well, some of these things seem to matter, and relative to our first one, we've got a little bit better fit, but again, it's not so great. And actually the nonlinear things with the polynomials seem to matter more than these interactions, because up here, remember, we had 7.9%, here we have 7.4%. You could go on and then include all of these things. You could include interactions and polynomials, and you could just keep adding more and more and more. We don't know what the actual right model is, so you try these things and see what works. Okay. Or alternatively, you have hypotheses and you try and test things. So we're going to do some other models here, and these are machine learning models. There's so much we could talk about, so I'm going to try and keep it as simple as possible and not go into all the details. I'm just going to try and show you the minimum that you need to know, and then if we want to talk about more, we can. We're going to use this carrot model. So here's, again, a website you can go to, list a ton of models. I want to use some regression tree models and a neural network model. So again, we can look at these things. I listed another website that kind of talks about one of the training methods that you can read about that and try and understand why we choose certain methods of training the data. And so there are lots of things you can fine tune here. But anyway, so I wanted to remind you these random start methods. If you haven't set the seed, then it can be totally different when I run it versus when you run it. And I already showed you this, removing temp2 and temp and temp2, so we won't do that now. We're going to work on one of the forest-based methods, the tree-based methods. And the first one we're going to use is called random forest, which just does a bunch of regression trees. And in order to do that, we're going to set up the parallel running of the machine learning. So this detect cores tells me how many cores I have on my machine. I have 8. You probably don't ever want to use all of the cores available because your machine can sort of stop working. Not permanently, but I mean use up all your memory. So I usually use 1 or 2 less than the cores I have available. You may not have that many cores if you don't have a desktop or something. It's okay. You can run this without doing any of this parallel stuff. So all you would do is remove these parallel parts. So if you don't do any of this, the rest will work just the same way. The only difference is it may take longer to run. And some of these things with the different parameters that are available could run a really long time. I've tried to set it up so it won't take forever, but it's possible it could take a while. Okay, so I'm going to run this. This 109 says create how many clusters you're going to allow your machine to use, how many cores, and then this is set up the parallel running, and it uses this thing. So, okay, so we run this. Now R will be running in parallel for anything that it can run in parallel, and if you run a package that can't do that, then it's not going to matter, but caret is set up for a number of models run in parallel. Okay, so then this is the random forest, and the function here is train. So that is a caret package function that is going to run through different parameters. So for example, how many trees is it going to use? How long is it going to let those trees run? That's this training part. We're going to leave most of everything else to the default values. Of course, we could go through and change those and fine tune those, which we'll do a little bit of next time. But we're going to run this random forest. Notice it's set up the same way as we have in the linear model. There are other ways to set it up as well and reasons to use one or the other, but we'll use this for now. Pull from the training data. The method that we're going to use is RF. RF is random forest. So this part here is just to remind you that there are other things you can use to control how the training actually works. So we run this, and you'll see on a bunch of these machine learning methods, it takes a while to run. So by the beauty of video, I'm going to stop it and come back when it finishes running. All right, so as a slight warning, the slowest running machine learning program that we're going to be doing or model is this random forest. So you may want to leave it running for quite a while. So even with the parallel method, mine runs for about a half an hour. So the other ones will be quite a bit faster. Anyway, so we run this. The problem with machine learning models is that there's not something that's easily interpretable. We don't have something that says, here's a slope, and we can see how much future revenue changes with current revenue. So there are a number of ways that machine learning models try and give you some information about it. Really, what we're going to do in the end is just say, does it have a good prediction or not? And how to evaluate those predictions is something we're going to spend most of our time on next class. So here, though, we're going to do one of the things that's useful. It's this variable importance. This is a function from the caret package. And notice I have this object that I saved that is the result of the random forest model. This is sort of like doing a summary of the random forest model. We look at the variable importance. What this tells us is the top one is the most important. And by that, it means how often is that variable used in the trees of the random forest. So revenue growth is used a lot in this version of the random forest. Liability growth a little bit less, asset growth a little bit less, and expense growth is not really used at all. XGBoost, that's extreme gradient boosting, which is another form of a tree-based model. So we won't go into the details of that, but it's sort of like a random forest. The main difference is that in the random forest you use random different trees. In this case, for the extreme gradient boosting, it's sequential trees where it keeps splitting the data in certain parts. So we can run that. And again, it will take a little while. We're going to look at the variable importance that comes out of that. If I have to, I will stop it and we'll wait, but it shouldn't be as long as the random forest, because the random forest has to run a lot of different individual trees, whereas in the extreme gradient boosting, it runs a tree and then makes some adjustments based on that tree. So we'll run it a little bit. Again, it's going to run using parallel processing, which will help a little bit in speeding it up, but it may still take a little while. So again, this didn't run quite as long as the random forest model, maybe 5 or 10 minutes. And here we have that the variables that are used in the random forest model are different from these that we see in the extreme gradient boosting model. Liability growth is the most important, revenue growth second, asset growth third, and then expense growth is still not used at all. Again, we haven't evaluated how good these predictions are, but now we have a model that has been trained on training data that we could potentially use. The last one is a neural network model. There are several different models that can be used in the Carrot package. From my experience, this one is the most common, but again, we will use the default methods and training parameters and run this. Again, this should run something like the XGBoost model, and we'll go ahead and run that and then look at what comes out of that. So the neural network model is a little faster, at least with the default values. Sometimes you'll get these warning messages, and some of those can be important. Other times they just show up because it ran into problems at one iteration. So we won't deal with these warnings in particular, but as we go to see how the predictions perform, that can give some insight as well. So we look at the neural network output. This one again has revenue growth as the top, but liability growth is the second, expense and asset growth. Notice expense growth actually mattered here and asset growth didn't. In principle, these are all doing the same sort of thing, trying to find patterns in the data that will work for explaining the revenue growth variable that we're trying to predict. But because they use different assumptions to pull out those patterns in the data, they come up with slightly different models and patterns, and so they likewise might perform differently when we go to do prediction. So at the end of this, I've done all of this parallel processing. I need to stop it, otherwise it's tying up my cores on my machine. So I stopped this cluster. CL is what we named it up here. Remember, we made these and then registered, meaning start the clusters. So down here, I'm going to remove that. Now it's back to running normal. And the big question that we haven't addressed then after we run all of these models is we have this random forest model, we have this XGBoost model, and this neural network model, and we see what goes into those models, but we don't have any idea how well they perform. When we had done these linear regression models, we at least have some idea on the training data how these perform. The next class, we're going to work on how to evaluate these predictions. So if you don't want to run it again, maybe you leave this open and save this, or just plan to run it again. So these predictions we're going to use, so this model here, EST, and this one, I should have named them separately, differently, so in the next one I will. But these estimations, these linear estimations, and these other ones, this training one, this training one, and this training one, we will use those objects to make some predictions and evaluate how good those predictions are.